Good afternoon, everybody. And welcome you to 10th session on SageMath. In this particular lecture, we are going to look at differential equations with Sage. So we will be looking at differential equations of order 1, 2, maybe system of ordinary differential equations, and we will also look at some applications. We shall also look at solving differential equations using numerical techniques. So actually, let me just first begin with saying that Sage has somewhat limitations in differential equations. Some of the inbuilt facilities that you can find in Sage are the following functions. One is DE-solve, that solves differential equations of first order and second order, and it uses maxima. You can also solve system of ODE using DE-solve underscore system. Then you can use DE-solve Laplace, that is solving initial value problem using Laplace transform. You also have facilities to do numerical solutions of ordinary differential equations using Euler method or using Rk4 methods, including system of ordinary differential equations. But one can also use DE-solve underscore ODEINT from SciPy integrate package, and there you will also be able to solve higher order differential equations. Of course, there are some more facilities, but we shall look at some of these things. So let us begin with a first order ordinary differential equation. So let us look at an example. Suppose we want to solve dy dx is equal to x upon x into 1 minus x upon y into 2 minus y. This is what we want to solve. Okay, now if you suppose the solution is yx, which is given by, let us say, implicitly in terms of x. So if you try to plot this curve, implicit curve, that is solution curve, at each point this dy dx at that point represents the slope. We have already seen this in calculus. We looked at what is geometric meaning of derivative of y with respect to x when y and x are implicitly defined. So first, one can plot what is the vector field represented by this, and then we can solve and then try to also plot the solution curve. So that is what we will look at. So let us see how we can first plot this vector field associated with this differential equation. So what we will do, we will first define x and y as variables. We will declare x and y as variables, and then define the right hand side of this differential equation dy by dx as f of xy, right? This is f dash xy is equal to 0. You can think of in this way. So fxy is equal to x into 1 minus x divided by y into 1 minus y minus 2. That's the differential equation, right? Now let us plot. So Sage has a function to plot slope field. Okay, this is called slope field. So then you just mention the function fxy and the domain of x and y, and let us plot this. Let us ask it to show, and when we execute this, this is what you see. This is what is called slope field. So if I look at a particular point, you'll see that how this solution passing through that point, how will it move in this domain. Okay, that's what it represents. You can also plot, we have already seen how to plot streamline. That means it will also plot a curve along with the direction. So let us add streamline plot to this, just to show that how these vector fields move. So we can use streamline plot with the same function fxy, x going from -2 to 2, y going from -2 to 2. Figure size is equal to 5, right? So let us look at that. Yeah, so this is what is called streamline plot. So basically it's a the solution curve, and tells how the solution is moving as we move along x, right? You can also try to plot both these things together, that is p2 and p1. Here p1 is the slope field, p2 is streamline plot. So let us add these two together and ask it to show p1 plus p2 figure size is equal to 5. So you can see here, you can just compare these vector field and the curve. So these are the solution curves. So for example, if I look at 0, if I look at, for example, this curve, this particular curve, then this is 0 at 0, y at x equal to 0, y is equal to 1. So if I try to solve this differential equation with initial value x equal to 0, for x equal to 0, y equal to 1, this is the curve you should get. Okay, we will verify this in a minute. Okay, let us look at how we are going to solve this in Sage. So as I said in the beginning, Sage provides a function called DE_solve, using which you can solve first order, second order ordinary differential equation, both including initial value problems. Okay, so let us look at how we can do. So general syntax for using this DE_solve is this: you have to mention DE_solve in the bracket, mention the differential equation DE, and then this D variable is dependent variable, and ICS stands for initial conditions, IVAR is initial independent variables, and you can also ask it to show the method that it has used. So that's a very good facility. Okay, so let us see how we can make use of this. But I suggest that you can take help on this. You can take help on DE_solve and go through this help document. This will explain how to make use of each of these parameter, and also it will give several examples. So you can go through. By now I'm sure you are comfortable taking help and going through the document, so I'm not going to run this in my system. You please look at solve DE_solve help document. Okay, so let us see how we can solve this. So first we need to declare x as a variable, and then y also as a variable, but y here is a function of x. So you have to say y function in the bracket, you write y inside single quote, and then it is a function of x. This particular syntax means that y is declared as a function of x. We have also seen how we can define a function, right? Of course, you should also keep in mind, in case you are using older version of Sage, this may be slightly different way in which it was defined earlier. Okay, so now let us declare the differential equation DE. This is equal to DIFF of y with respect to x, that is derivative of y with respect to x, and that double equal to fxy. Fxy we have already declared as the right hand side of this differential equation, that is x into 1 minus x divided by y into 2 minus y. Okay, so that's my differential equation. Now in order to solve this, you have to call DE_solve and then say what is the differential equation, and then mention what is y. Remember that this these two ICS, that is initial conditions, and independent variables, show methods, etc., are all optional, so you need not mention to begin with. Okay, now let us solve this and see what is the solution we are getting. So the solution is minus 1 by 3 y cube plus y square is equal to 1 by 3 x cube minus half x square plus a constant c. Here you should also notice that here instead of c, it is saying underscore c. Okay, this is again a variable. This is just to distinguish the variable that user would have defined and the variable that is coming from the inbuilt facility, inbuilt functions. So that is why Sage puts underscore c for variables. Okay, so let us look at, you can ask it to show, when you ask it to show this, then underscore will not be there. So that is how it looks like. So this is the solution of this differential equation, which is implicitly defined in x and y, and we can plot graph of this the solution curve. Now let us put initial condition to this differential equation. So let us say, we say y at 0 is equal to 1. Okay, y at 0 is equal to 1. We already know from this from this streamline plot or plot vector field how this solution curve is going to look like. So for example, this seems to be y equal to 1, so this is how the curve will look like. But let us see, let us verify the same. Okay, so this is the differential equation. Now let us put initial condition. So initial condition, so again I'm calling this as solution 2. D is solve, and then differential equation with respect to dependent variable y, and the initial condition one has to give as a list. In this case there are two things, 0 and 1. 0 means x at 0, and 1 is x at 0, and 1 is y at 0. Okay, so this is actually x0 y0. Okay, now let us see what is the solution. So this is the solution you got. Okay, now let us plot this graph, plot this curve, and see what we guessed is correct or not. Okay, so let us plot this function. So this is just a slightly crude way of plotting this, in the sense I'm just since here it is yx not y, so we will replace wherever yx is there by z, but you need to declare z as a variable. So this solution is implicitly defined, so we will plot this implicitly defined function of this solution curve, and let us plot along with p1, which is the vector field. So now you can see here that's the solution curve. Okay, that's the solution curve. Let me ask at this stage one more question. In case I change the initial condition, suppose instead of y0 equal to 0 I say y0 is equal to half, then how will the solution curve look like? Of course it is quite clear, it is quite easy to guess what will the solution look like. However, let us see, but do you think that these two curves will intersect? That I'm sure you know the answer already, this will not intersect. Okay, so let us try to solve differential equation with initial condition x0 is equal to 0.5. So I'm just calling this as solution 3, and then let us look at what is the solution look like. This is how the solutions look like, and let us plot this along with the initial value x equal to at 0 it is 1, at and the second one at 0 it is half. So the green one is the solution of the second initial value problem, which is x at 0 is equal to half, and this blue one is x at 0 is equal to 1. So you can see here these two curves do not intersect. So in fact you must have seen in your differential equation course that any of this the solution curve will not intersect. Okay, so this is a simple example. Let me give you another example. I am sure you must have seen this is a model which is quite popular among population model. This is called logistic population growth model. Okay, so the population, the rate of change of population is proportional to p into 1 minus p upon k. That is what is called logistic population growth model, and here k is called carrying capacity and r is called growth rate. Okay, so let us try to solve this and see how the population grows for various values. Okay, so let us define this differential equation, and let us take the r, that is the growth rate of this population is equal to 3 by 100, and the carrying capacity is 1500. Okay, so think of this is population of some small species, right? Okay, now let us solve this differential equation. So again, t and p has to be declared as variables. P has to be declared as a function of x, as we did earlier. Y as a function of x. Here I'm thinking in not x but t, the t as a time. Okay, now so let us define differential this solution. This is so differential derivative of p with respect to t. This is equal to r into p into 1 minus p upon k, and we solve with respect to variable p, and the initial condition let us take as 200. So initial population is 200, and let us see what is the solution looks like. So this is the solution. Okay, So it is minus 100 upon 3 into log pt minus 1500 plus 300 by 3 log pt is equal to this. Now if you look at this solution, everywhere you can see there is, it is multiple of 100 by 3. Okay, so let us divide this by 100 by 3 and try to simplify. So let us look at, instead of solution, let us look at solution into 3 by 100, that is dividing by the common factor is, let us cancel it out, and then we can solve this for p. But this equation is in log, so that is why it says also has a facilities to solve uh, for log, that is called simplify underscore log. Okay, there are simplify underscore trig, and then are full simplify, and other things are there, so you can look at, and as I'm calling as solution t, SOLT, and now see what is the solution look like. So this is the solution. P of t is equal to 3000 into e to the power 3 by 10 divided by 2 into e to the power 3 by 10 plus 13. That's the solution. It is explicit in t. Now let us plot graph of this and see how the solution or population growth model looks like. So we can plot solution. Now you can see here that when we have said this solution, it is a list of list in which pt is equal to the right hand side. So if I want to extract this right hand side as a function, I have to say first look at the 0th term, that is you remove the square bracket, then what you are left is left hand side and right hand side. So then take the right hand side of this I mean, I'll simply, let me run this here so that it will be clear what I mean. So when I say solution t0, it removes the square bracket. Okay, so this is the first term of the list, and then we'll say dot RHS, the right hand side, so then it will show only the right hand side part. So that is what I'm using. So plot this and see how the solution looks like. So you can see here, so it starts from 0, it keeps on growing, and then around 1500, which was the carrying capacity, it stabilizes, right? So that is how the population model curve looks like. You can try to plot this population curve by changing the initial conditions and the carrying capacity, etc., just to see how it changes. So this is stabilizing around 1500. Let me add horizontal line at y equal to 1500. So here itself I'll add, so I'll say plus plot what 1500, the carrying capacity, or let me say k here, which I have already defined, and t varies from 0 to 300, and let me put dotted line, so line style is equal to inside double quote dash dash hyphen hyphen, and then let me also put color is equal to, let us say black, let me put green, okay, in single quote or double quote. Okay, so yeah, that's the carrying capacity, and you can see here the population will not grow beyond this carrying capacity. That is what it means. Okay, so this is an application of a simple ordinary differential equation, and yeah, okay. So many times you would like to plot graph of several solutions together for various initial conditions. So here we did two of them for a x0 is equal to 1 and x0 equal to a half. But suppose if I want to do multiple and use some kind of loop, then also you can do this. So let me just explain this with a small example. Let us look at another differential equation. Log y is equal to dy upon dx is equal to y into sine x. And so let us solve this. So I'll not explain this all these syntax because already we have used it. So that's the solution. And then you can see here there is one integrating constant here, that is minus c. So that minus c, you can obtain what are the constants by using this notation. So solution under dot variables will tell you what are the variables that it is there in the solution curve. Okay, so here in this case there are only one c and the variable is with respect to x. So if I want to extract c, I have to say this of 0, so that is this. Now what you can do is this I have explained already. So now let's solve this with for y, since this is explicitly defined in y, we can solve this for y. And then once you have done this, then then let us look at the first solution, and then let us substitute this capital C by small c. This means in the solution the solved with respect to y, and the first part inside this you substitute c is small c is equal to equal to 5. So whatever you want you can substitute, and then this is how the solution looks like. So this is a special case where c is taken as 5. Now you want to do this for various values of c at a time. So how will you do? So yeah, so you can plot this curve. So that's the plot for c is equal to 5. Now let us say we want to do this for various values of c, and let us say c varies as 1 plus k by 4, where k going from 1 to 19, where let me say 1 to 21. So k will take value 1, that is c is equal to 1 plus 1, then c is equal to 1 plus 1 by 2, and so on. And all of this will be plotted. So in the beginning it is starting with empty graphics, right? Or you can start with a list and then append all these things in this list and then add. Or you can use this facilities, p is equal to graphics, and then inside this you keep on adding, and then try to plot what is capital P, which you have got. So you can see here several solutions are plotted, all of them together, and again you can see here that no two will intersect. Okay, so that's solving first order ordinary differential equation, including the plotting solution curve, plotting the vector field and our slope field, and plotting the various curves, including the analytic solution. Now suppose you have a second order differential equation, ordinary differential equation. Let us say 4 into d2y upon dx square plus 4 dy by dx plus 17y equal to 0, where y at 0 is equal to -1, y at 0, y dash at 0 is equal to 2. So then in this case, again defining this differential equation, you have to simply say d is solved, and then 4 times it's a derivative of y with respect to x twice, that is second derivative, plus 4 times derivative of y with respect to x, and then plus 17 double equal to 0, solve with respect to y, and then give the initial condition. So here this initial condition means that at 0 x equal to 0, y 0 is -1, and at x equal to 0, y dash 0 is 2. That is what you have. Okay, so let us solve this differential equation. This is what you get. This is the solution, and you can again you can plot this. So this is how the solution looks like. Okay, and then you can, but if you don't mention the initial condition, then it will give you solution in terms of two constants k1 and k2, and again you can find out what are the constants here, the variables. So namely it is underscore k1 underscore k2 and then 0. So again, if you want, you can plot the solution curves for various values of k1 and k2 and see how this solution changes, right? So you can use the same DE solve to solve first order ordinary differential equation as well as second order ordinary differential equation, both without and with initial conditions, right? Just I would like to mention, in case your this were a boundary value problem, suppose x y at 0 is something and y at 1 is something, then also then you need to give this as a list. I have to say 0 1 and then 2. So 0 at x equal to, sorry, just 1 second, yeah, at x equal to 0. So you have to mention these four things, namely x1, x2, y1, y2. Okay, so that is what you can look at the help on this. It will give you also an example. Okay, fine. You can also solve non-homogeneous equation. So if I have to solve this non-homogeneous equation, right, then also you can solve using the same function, namely de solve, and just mention this differential equation. And let me also in this case say that what is the method it is using. Show method equal to true. So in this case it uses variation of parameters. Let me remove show, so that was solution. So this says that it uses, this is the solution, and it uses variation of parameters. That's the method it uses in order to solve this differential equation. Okay, now let us you can even uh, define what is the auxiliary equation related to this, but there is no inbuilt function to do that. You have to manually define. That is, in this case it is m square minus 4m plus 4, and if you solve this auxiliary equation, there is only one solution, namely 2, which is repeated. So in this case the solution will be e to the power 2x, one solution, and other one will be x into e to the power 2x. And you can find Wronskian of this. So there is an inbuilt function to find Wronskian, and Wronskian in this case will be non-zero. You can see here, this is the term, so this will never become 0. This is always positive. This is always non-zero in this case. So these two solution, that is e to the power 2x and x into e to the power 2x, both will be linearly independent. So of course I encourage you to possibly solve this step by step, as you do in your notebook. That is you can find the solution of the associated homogeneous equation and find a particular solution, and then take sum of these two and see whether this is same, whatever you are getting is same as the one which is given by the inbuilt function. Okay, right. So this is, let me just give you briefly one more example. This is again second order differential equation. X double dash t is equal to omega square x plus f naught into cos gamma t. X0 is equal to 0, x dash equal to 0. And so here this omega and gamma are constants. So in case you take omega and gamma is equal to 2, this is what is called forced undamped spring with resonance. Whereas if you take omega equal to 2 and gamma equal to 3, this is undamped. Okay, so I'm sure you must have heard about this collapse of Tacoma Narrow Bridge, which collapsed after 4 years of its inauguration. And there were initially there were few models, and this equation to some extent explains why this incident happened. So you can let us look at how one can solve this. So again, it is the same thing. I don't want to repeat. So you just mention the differential equation. Now in this case, differential equation I have defined using lambda, right? Or you can declare left hand side and right hand side, and you have used f0 is equal to 1, omega is equal to 2, and g is equal to 3. So in this case the solution, this is how the solution looks like. However, in case we take omega is equal to and gamma is equal to 2, this is how the solution looks like. So you can see here the frequency is increasing, and in this case this is what you happen. So in depending upon omega and gamma, you can see that the solution curve differs quite a bit. Okay, so there's another. Now let us move on to how we can solve system of ordinary differential equation, linear ordinary differential equation. So let us take an example. Suppose you have first equation as x dash t is equal to minus 5x plus 2y, and y dash t is equal to x minus 4y. So these are the two system of ordinary differential equation. Suppose if you want to solve this, again x, y you have to declare as a variable, x as a function of t, y as a function of t, and then you define first equation, define second equation, and then you can use de solve underscore system. So that is what we have to use. So again you can see here t is a variable, x and y are declared as function of t. The first equation I'm calling as de, which is derivative of x with respect to t, is equal to minus 5x plus 2y, and second equation dE2 as derivative of y with respect to t double equal to x minus 4y, and then let us call this system as DES, and then solve DE underscore solve. What is the system you want to solve? DES, which is the first equation, second equation, and with respect to variable x and y, and let us see what is the solution you get. Okay, so this is the solution in this case. Of course, the solution will be in terms of x at 0, y at 0. So that is what you can see here, right? So now let us I mean, you can print this solution separately. You can ask it to show what is the x coordinate, y coordinate, in this case x and y. And if you want to solve this initial condition, right, solve this with initial condition, let us say x0 is equal to 0, y0 is equal to 0. Again, all we need to do is here we need to introduce initial condition. So let me just do that. So this is the next part. So again, this is the same thing as earlier. So here extra thing is introduced as initial condition 0, 0, 1. So this means x at 0 is equal to 1, is 0, and x y at 0 is equal to 1. Okay, that's what it means. And then let us solve this. So this is the solution you get. You can even plot this solution as a parametric plot. So let us extract this, each of this x and y, and then okay, this is not required. So here this is just checking that y at t equal to 0 is 1. It is correct. If I say solution x at t is equal to 0, it should be 0. And now let us plot this using parametric plot of x and y. So this is the solution curve of this system of ordinary differential equation. Okay, fine. Now let us take an example of, suppose you have 3 equations in 3 variables. How do we solve this? So I'm sure you must have looked at this. Can be also solved using a notion of eigenvalues, eigenvectors. So that is what we will look at. So you can think of this as one more application of eigenvalues, eigenvector. In fact, purposely in application of linear algebra, I skipped that part so that I could include this in this particular differential equation. So let us go to the next example. So you want to solve a system of ordinary differential equation x dash is equal to a times x, where a is, let us say 0, 0, minus 2, 1, 2, 1, 1, 0, 3, and initial condition, this is 1, 2, 3 at x equal to 0. So here x1, x2, x3, x is column vector x1, x2, x3, right? So you have 3 equations in 3 variable. First equation is x1 dash t is equal to minus 2 x3 t, x2 dash t is equal to x1 t plus 2 x2 t plus x3t, and so on. Okay, so this can be solved using now the solution will depend upon the nature of this a. So let me put it, give you 2 examples where the case in which a is diagonalizable, and the second one when a is not diagonalizable. In that case, we will use Jordan canonical form of a and find the solution. Okay, so that's another use of Jordan canonical form, and Sage has inbuilt facilities to find Jordan canonical form, which again I did not do it in linear algebra, but here I will just do it for you. Okay, so how we can solve this? Let me just briefly explain what is the strategy that we are going to adopt. So this differential equation is x dash equal to ax. In case a is diagonalizable, that means there exists a matrix P, non-singular matrix P of eigenvectors, such that A can be written as P D P inverse, where D is diagonal matrix of eigenvalues. Now put this A in this differential equation, so x dash will become P D P inverse x. Now multiply both sides by P inverse. The left hand side will become P inverse x dash is equal to D times P inverse x. So in case you substitute P inverse x is equal to, let us say, z, then this differential equation, then z dash will become z dash will become actually P inverse x dash. So therefore left hand side becomes z dash is equal to D into x dash. So now D is a diagonal matrix, so it's a constant matrix actually, right? So therefore the solution and the solution of this can be obtained exactly in a similar way as you have done finding solution of dy by dx is equal to, let us say, constant times x, right? So I think there is small problem here, so this is should not be dash. Okay, right. So in this case the solution will be z will be e to the power dt, d times t, d is diagonal matrix. So exponential of this diagonal matrix we are taking, exponential of diagonal matrix will be just exponential of the diagonal entry, the matrix whose diagonal entries are exponential of each of these diagonal entries times z naught, right? And then if you substitute z naught, what will is z naught? Z naught is equal to p inverse x naught. So if you substitute this, you will get the solution. Okay, so that's the very simple way of finding solution in this case. So let us execute. So first let us find out solution of this system using inbuilt function, using desolve system. Okay, desolve underscore system. So again, how we are doing, we are declaring t as a variable, x1 x2 x3 as a function of t, declare first equation, second equation, third equations, right? And then solve using desolve of the list of three equations with respect to variable x1 x2 x3, and initial condition is here initial condition is x0 equal to 1 2 3. So you have to say 0 comma 1 comma 2 comma 3, and the independent variable is t. Okay, so let us look at how the solution looks like. This is how the solution looks like. Let me ask it to yeah. So the first x1 is minus 7 e to the power 2t plus 8 e to the power t, x2 is 6 e to the power 2t plus minus 4 e to the power t, and x3 is 7 e to the power 2t minus 4 e to the power t. Okay, now let us look at how we are going to do this. So as I said, we will need to diagonalize this matrix in case it is diagonalizable. So in this case, let us look at, this is the matrix, and x naught I'm calling as a vector. Now so Sage has an inbuilt function to find eigenvalues, eigenvectors. We have seen already this, but you can also find eigenmatrix. So a dot eigenmatrix underscore right will give you diagonal matrix of eigenvalues along with the matrix P, okay, of eigenvectors. So let us see. So P is this one. So it has two eigenvalues, 1 and 2. 2 is of multiplicity 2, and there are three eigenvectors here. You can see this matrix is invertible, so that's your P. So therefore this matrix is diagonalizable. So once it is diagonalizable, then what we can do, and we can check whether A times P is equal to P times D. That is true. So now what we can do, so here the solution, you can see here what is the solution going to look like, P into e to the power dt. So e to the power dt will be the diagonal entries d1t, d2t, etc., and then P inverse x naught. So let us write that. So I'm just defining dt as diagonal matrix. That first diagonal is t, second one is 2t, third one is again 2t, and then exp et is equal to exponential of this. So Sage can find exponential of a matrix. So this exp again can be used for the exponential, and then define y is equal to p into exponential of t, that is exponential of dt, into p inverse, right, and multiply that by x naught, and that should give you the solution. So if you compare this with the original one, let me just print what the solution we got, so that we can compare here itself solution. So you can see here the first coordinate is minus 7 e to the power t plus 8 e to the power t, and that is same here. So the two ways in which we have solved, one is using inbuilt facilities, and other one using diagonalization. Okay, now the next question is, in case the matrix is not diagonalizable, then what will you do? So in that case we use Jordan canonical form. Okay, and and we know that every matrix has Jordan canonical form. Of course, you must have already gone through the theory, so you know all this. I'm not going to explain this. So let us look at another system of ordinary differential equation. X dash is equal to ax, and a is equal to 2 1 1 2 1 minus 2 minus 1 0 2, and x0 at 0 is 8 32 5. Okay, so in this case we will look at, so let us look at first what is the solution using inbuilt function. So in this case, let me print what is the solution. So the solution looks like this: x1t, x2t, x3t equal to this. Okay, and okay, fine. So this is in matrix form. Okay, now let us look at how we can solve this using Jordan canonical form. So here we know that this matrix, suppose we split A as P, J, P inverse, where J is Jordan canonical form of A, and this will be consist of the block matrices, where each block is a Jordan block. Okay, so so the change in this and the previous one, instead of D, you have J here. So if it knows how to find the exponential of J_t, then you are done. And Sage can find out exponential of a Jordan block. Okay, so that is what we will be using. So now let us look at, suppose this is the matrix A. Let us find out eigenvalues and eigenvectors. So this again has two eigenvalues, one 3 of multiplicity 1 and another one is 1 of multiplicity 2. Let us see whether it has enough eigenvectors to be diagonalizable. So in this case, the eigen matrix of this is 3. This is the matrix, which is, you can see here, it is non-singular matrix. So the last column is 1. Therefore, this matrix is not diagonalizable. Okay, so in case this matrix is not diagonalizable, we can find its Jordan canonical form. So there is an inbuilt function to find Jordan form, that is A dot Jordan underscore form, and you have to say use transformation is equal to true. Of course, you can look at help on Jordan form and see what are the other options available. So let us and then it will print both the things, J, that is Jordan canonical form, and the matrix P. Okay, so let us run this. So this is the Jordan block canonical form of this. This is one block, this is another block, and this is the matrix P, right? So now let us this is not needed. Let us get rid of this. This is, let us verify P inverse AP is equal to J or not. The answer is true. That's correct. So we have got this correct Jordan canonical form. And now let us find out what is exponential of J of Jt, J times t. So in this case, exponential of Jt will be e to the power 3t, e to the power t, t e to the power t, and e to the power t. And then once you have done this, then this is your initial matrix, and then let us find the solution. So the solution is P into e to the power Jt into P inverse times initial vector. So let us multiply this by initial vector and see what is the solution you got. This is the solution, and you can see here this solution will be the same as the previous one. Let me see how, yeah, this one. So let me ask it to print both these together so that you can see here. Yeah, so that one I called as solution X. Let me print this as this, so you can see here both these things are matching. So this is how you can solve using Jordan canonical form system of linear ordinary differential equations of order 1. But in case you have a higher order, you can always convert into system of first order. Okay, I just mentioned that Sage can find exponential of Jordan block matrix. So that is you can very easily explain. So you must have seen in the theory part, if this is a Jordan block, then exponential of Jt, how it looks like. So one can prove this using induction. And let us see. So let us take a Jordan block. So let us see, this is a 6 cross 6 Jordan block. So diagonal entries are all A is a variable, then above that is all 1 1. And if I want to find exponential of this is how we'll get that justifies this, verifies this result for A and T, and for N is equal to 6. Okay, right. So this is how we can solve system of ordinary differential equation using diagonalization technique or using Jordan canonical form approach. Okay. Next, let us look at some example of solving numerical ordinary differential equation numerically. So let us look at this example. Dy dx is equal to 1 minus 20y, where y at 0 is equal to 0. We want to solve this using two methods. One is using Euler's method, and second one using Rk4 method. Okay, and in the interval 0 to 2 with a step size 0.1. Okay, so let us define this differential equation again in the same way. So t and y are declared as variables. F is equal to 1 minus 20y, and then solve. First, you can plot this solution field, the slope field of this differential equation. So this is how it looks like. So if I say y equal to y0 is 0, the solution will look like something like this. So it will be something like this and this. Okay, so we'll just verify that. Okay, now let us solve this differential equation again using the same way, and then plot the solution. So this is how the solution, exact solution, this is how it looks like. The exact solution is 1 upon 20 e to the power 20t minus 1 into e to the power minus 20t. That is how the solution looks like. Okay, so here the initial condition is y0 is equal to 0. This is how the solution looks like. Now let us superimpose the solution obtained using Euler's method. So if I'm using Euler's method, then you have to use Euler's underscore method, and you need to mention the differential equation, the right hand side of the differential equation, initial point that is 0, and then initial condition that x0 is equal to 0, that is what is given here, y0 is equal to 0, so that is the one. And then in the interval from 0 to 2 and with the step size 0.1. So this is an algorithm, let it use the default algorithm. Okay, and then the solution it will produce as a set of points xi yi. Okay, xi yi, right, between 0 to 2. So it will be 0, then 0 0.1, 0 0.2, 0 0.3 up to 2, and then the corresponding solution of y. Okay, so let us put this and plot this as a line. So that is how it looks like. You can see here this solution and this solution looks quite different. So let us superimpose both this. So this is the original, the exact solution. This is the solution using Euler's method, and you can see here both these things are quite so error is quite substantial. Now let us solve the same thing using Rk4 method. So if you use Rk4 method with the same initial conditions, etc., this solution looks like this, which is very realistic, close to the original one. So again, you can superimpose all these three together and see here, right? So you can see here in this case Rk4 method works much better than Euler's method. Okay, and you can look at this with the different examples. Okay, so in this case again we are using solve Rk4 differential equation with respect to which you want to solve, that is y, the initial condition, and then what is the step size, and end point is equal to 2, that is 0 to 2 in this case we are solving, right? You can also solve a system of initial value ordinary differential equations initial value using the same Rk4 method. So here is a small example. This is called SEIR epidemic model. Nowadays, if you look at in this corona business, lots of people have modeled this corona epidemic using this SIR model or SEIR model and various other models. So I thought I'll just take this as one of the application. So here in this case, you have four differential equations, four system of equations in four variables x, y, z, and w. So x, y, z, and w are susceptible population exposed to the disease, infected one and recovered one, and beta, gamma, beta, sigma, and gamma are parameters. Beta is called the infection rate of the disease. Sigma is known as transition rate of the exposed individuals to the infection, and gamma is called the mean recovery rate. Okay, so if you go through the literature, in case you're not aware, you can see more details on this. So let us try to solve this. So here I have made a user defined function. Okay, so this is the initial condition for each of these four parameters, that is s init, S for susceptible, E for for exposed one, I for infected, and R for recovered, right? And beta here we have taken as 2 into 10 to the power 6, gamma as 1 by 14, and sigma as 1 by 10. And then this system is defined, and then you are solving using DE solve Rk4 method. Okay, and then all these conditions you apply, and then try to solve for each of these: plot S, plot I, plot E, and plot R, and all of this together. And let me call this function. So I have to input what are the initial conditions, and let us call this. So SEIR model, the initial S init is 45,400, and E init is 9,000, 31,000, the next one 25,000, and 200 in this case is these are the four things. Yes, now let us plot this. So when you plot this, you will see that these four curves are there, susceptible to the disease. You can see here that is increasing, so almost entire population will be susceptible at the end. And then this susceptibility is decreasing. I'm sorry, this is the red one is the susceptible. So initially this it is going on decreasing. This black one is recovered, so it is recovering. Almost everybody has recovered, and then other one exposed and infected. Okay, similarly you could also use another this in solving what is called Lotka-Volterra predatory prey model. This is given by this. So let me just show you. So again, this we are using DE solve system of ordinary differential equation using Rk4 method. So again, you plot this the xi y I t xi t y I and t z I. So here P will give you the 3 points, list of 3 points. Okay, you can and then you can plot one let us say x versus t. So here you can think of x as rabbits and y as wolves. So initially the 10 rabbits and 4 wolves are taken into the consideration in this population. So let us plot this. So that is how the curve looks like for rabbits, and then if I look at the wolves, this is how it looks like. Okay, and both this put together, that is the interaction, this is how the population will proceed. Okay, let's take, yeah, so you can see here somewhere there will be equilibrium around 6 rabbits and 3 wolves in this case, right? Okay, so there are many more examples that you can look at, including something in 3 dimension. So here there is a Lorentz system of equations, again similar to the previous two. So I'll not get into this, but quickly let me move on to, in the meantime let me just also run and show it to you. Okay, let it run. So next we are going to consider solving ordinary differential equation using Laplace transform. So Sage has facilities to find Laplace transforms of various standard functions. It also has facilities to find Fourier series. Unfortunately, yet they have not developed how to find Laplace transform, but you can work it out with a little bit of this programming language. One can easily find out. So you can solve you can solve differential equation also using Fourier series, especially the partial differential equations, etc. So let us look at how we can apply Laplace transform to solve a system, solve a ordinary differential equations, initial value ordinary differential equation, including the system of ordinary differential equations. Okay, so let us first look at how this we can use Laplace transform. So suppose you have a function, let us say you want to find okay, this plot is coming up now, yeah. So that is how the plot of this Lorentz equation looks like. You can, so this is a quite a chaotic model actually, yeah. So fine, it takes little while. Okay, let me go down. Yeah. So suppose you want to find Laplace transform of function t, right, in terms of parameter s. Then you can simply say ft is equal to t and f dot Laplace of the parameter is t, and then s, t and s are. So it say that Laplace transform of f of t is equal to t is equal to s to the power minus 2. Similarly, let us say Laplace transform of sine t is 1 upon s square plus 1. Laplace transform of cos t will be 1 up s upon s square plus 1, and so on. You can keep on doing, including if you have piecewise defined function, then also you can find its Laplace transform, right? Okay, so now let us look at a simple ordinary differential equation initial value. So let me go to the next example. Let us work out this one. So we have differential equation x double dash t plus 2x dash t plus 2x is equal to e to the power minus 2t. X0 at 0 is 0, x dash at 0 is also 0. We want to solve this using Laplace transform. So the way one solve this using Laplace transform is that you take Laplace transform of both sides of this differential equation, and then this Laplace, when you write this Laplace transform, it will get transformed into linear equation. Then you solve for that equation and then apply inverse Laplace transform. That's the basic idea. So let me just look at that step by step, and then we will solve using inbuilt function. Okay, so what we will do, first we declare this Laplace this differential equation. So second derivative of x with respect to t plus 2 into second derivative of f with respect to t plus 2x is equal to e to the power minus 2x. And then now let us take Laplace transform on both sides. So LTDE is Laplace transform of differential equation with respect to variable t and s. So when you take Laplace transform of both the sides, this Laplace transform of x double dash t becomes s square into Laplace transform of x t with respect to x and s, then plus 2 times s into Laplace transform of x minus s into x0, but x0 is given, plus and so on, right? And the right hand side is the Laplace transform of e to the power minus 2t, which is 1 upon s plus 2, and this particular term represents the derivative of x with respect to first derivative of x with respect to x at x equal to 0. Okay, so that's the, now what we are going to do is we will actually replace this Laplace transform by some variable, let us say capital X. That is why we have declared here capital X. So let us do that. So what we are going to do, so first convert this equation into string. That is the meaning of strLTDE, string. Convert this into a string and then replace this double quote Laplace XTTS by capital X again as a string. So that is what it is done. Now let us print what is this strLTDE. So that is how you can think. Now you see that Laplace transform has been replaced by capital X wherever Laplace transform is. Now what we will do, we will replace x0 by 0. That's the initial condition. And then derivative square bracket 0 x 0, that is x dash at 0 is equal to also by 0. So we will again replace it by derivative of x0 of x0 by 0. Now you can see here, now everything has become an equation in capital X. This is a linear equation in capital X. So but then this is still a string, so we need to convert that into expression. So Sage has a facilities to convert that into expression using Sage evaluate, and then we are saying string this, and wherever you have character s, you replace it by small s, and capital X you replace it by capital X, and then this is how it looks like. So this is a linear equation in capital X. Now you solve this for capital X. Now let us solve this for capital X. Okay, so this is solution using this is x in terms of s. So you can even take the partial fraction of this and then guess what should be the now we have to take the inverse Laplace transform of capital X. So if you this is the solution, the right hand side part of this, that is I'm calling as capital XS. And then let us take Sage also has facilities to find partial fraction. So partial fraction of this, now you can guess what should be the inverse Laplace transform of this, but let us use Sage to find the inverse Laplace transform of XS, and this is what you get the solution. So solution is minus half cos t minus sin t into e to the power minus t plus half e to the power 2t. Let us verify that this is same as what we get using inbuilt function. So if you use de Laplace, so there is a function called de solve underscore Laplace to solve this differential equation using Laplace transform, and you just mention the initial condition. So let us run this. You can see here this is same as what we obtain by solving this step by step. Okay, so it is good idea to always solve this using step by step, so also exactly you know what you are doing, and then you can verify using inbuilt function. Okay, similarly you can solve system of linear equation, ordinary differential equation of order 1 using Laplace transform. So here is small example, so let us see how we can do it. So again you define this two differential equation de1 de2 and then try to solve. So you can use de solve underscore system. So this is using inbuilt function. Of course it doesn't use Laplace transform. Okay, so if I want to use Laplace transform, what will you do again? You just take Laplace transform of both these equations, right? And then those two equations will become a linear equations in x, Laplace transform of x and Laplace transform of y. So it will be linear equation, two linear equations in two variables, let us say capital X and capital Y, and then you solve that for capital X and capital Y and you apply inverse Laplace transform. That's all. So it is very simple again, and of course you have to replace this initial conditions. So let us do that for each of these differential equation. So I will not run step by step. Okay, so this is the solution using inbuilt function. Okay, so let me just plot also. So this is how the solution curves look like. Now let us apply Laplace transform to each one of them. So first is differential equation 1, applies Laplace transform, and all these steps that I did in previous one, I have combined this together in one. And then when you solve the first equation, when you take the Laplace transform of the first equation with initial conditions etc., this is the equation you get: x times s plus y minus 1 upon s minus 1 is equal to 0. And similarly you can do it for second equation, that is this. Now you can solve these two equations simultaneously. So these are two linear equations in variables x and y. So solve this for capital X and capital Y. Okay, that's the. Now let us print what is the solution. Take the inverse Laplace transform of each of these. So the first coordinate here is 1 minus sin t, second coordinate is cos t plus 1, and that you can verify that's exactly what you would have got in this case using inbuilt function, right? So again we have verified solving this system of ordinary differential equation using Laplace transform. Okay, and you can try for partial differential equations. Okay, so I'm almost done everything here. Okay, so in this case I have just tried to give you a brief idea of solving ordinary differential equation, including the system of linear differential equations of order 1 using Sage, and also bringing out the geometric meaning of the solutions and various other things. And then I also gave several applications, real life applications like epidemic model or population growth and things like that, or even the the bridge problem, right? So try to solve as many problems as you want, but at the end, let me just also tell you, you can look at this book. uh, there is a book by David Joyner. It was written in 2011 using so this is introduction to differential equation using Sage. Joyner is actually one of the co contributor of this Sage, and you will see that when you see the help manual on DE Solve, you will see his name as a contributor. So you can go through this. So this book will also in fact, some of the examples I have taken from that this book, and you will also see one or two examples of solving partial differential equation with Sage. However, still it is not that much developed, but it has capability, and with little bit of programming language one can also apply to partial differential equations as well. Since I have not given course on differential equations, etc., so I don't have too many examples. But if you are interested, you can look at this book and try to explore more on solving differential equation using Sage. Okay, so thank you very much. These are the some of the assignment problems. So I will post it on the app. So let us say by this evening you should get it. Okay, so thank you very much. The next two lectures will be on group theory, and we'll try to cover most of the first course in group theory, the basic parts. Okay, so see you on this Wednesday. Thank you very much.